Okay, Chapter 3, Stoichiometry. This is Section 10. This is actually the last section of Chapter 3. And this covers stoichiometry, limiting excess, and percent yield. Again, everything you've had in first year chemistry. And stoichiometry is a lovely little German term that deals with the relative quantities of reactants and products in chemical reactions. Reaction stoichiometry. First, you need a correctly balanced, note the word correctly balanced. You cannot do proper stoichiometry unless your chemical reaction is balanced appropriately. So always remember to balance it. You have to have a correctly balanced chemical reaction. They tell you the mole ratio of one substance to another. It's the number of moles of a reactant to product, reactant to reactant, not mass of. Stoichiometry is a way to mathematically calculate the mass of a product given the quantity of reactant. The mass of the product is considered the theoretical yield. It's also used to mathematically calculate the mass of one reactant needed to react completely with another reactant. There are going to be a variety of problems for stoichiometry. You could do a mole to mass, given the moles of reactant number 1, what mass of reactant number 2 will react completely with it. It could be a mass to mole, given the mass of product, how many moles of reactant did you start with? Molecules to mass, that's Avogadro's number. Mass to mass, mass to molecules. You might be comparing a reactant to another reactant. You might compare a product to another product. You might go reactant to a product, which is theoretical yield, and you might be comparing a product to a reactant. So that's a huge variety of types of problems under the heading of stoichiometry. And later on, we'll be doing stoichiometry with energy, and we'll be doing it with gas laws and volume and stuff like that. So stoichiometry all the way through chemistry. So here's an example. This is called the Haber process. Let's see if I can fit this in. This is called the Haber process. This is the production of ammonia gas, big in the fertilizer industry. The Haber process is nitrogen gas reacting with hydrogen gas to produce ammonia or nitrogen trihydride gas. It is already balanced for you. How many moles of ammonia can be produced from 14.3 moles of hydrogen gas, assuming excess nitrogen. Now, this is important for this type of question. This guy is exceedingly important. This guy is important because it tells you that one of the reactants is in excess. What it tells you also is that this is not a limiting excess problem. And I'm abbreviating it, but you've done this before, so you should know what I'm talking about in some way, shape, or form. All right, so here's what we're going to do. This is a nice, simple one. We start out with the number they give me in the problem, which is 14.3 moles of the hydrogen gas. From the balanced chemical equation, find out what the ratio is for ammonia to hydrogen. According to the balanced chemical equation, 2 moles of ammonia will be produced for every 3 moles of hydrogen gas. This ratio right here is the stoichiometry part. these two numbers will come from the coefficients in your correctly balanced chemical equation. Now, since the question's asking you how many moles of ammonia it is, that's it, one ratio. Now, concerning sig figs, we're going to make life easy. If there's a decimal, consider it a measurement. Therefore, 3 sig figs here, 3 sig figs in my answer, and I'm done. Still using the Haber process. And this time, it's a mass-to-mass situation. They're asking you what mass of hydrogen gas is needed to completely react with a quantity of nitrogen gas. A couple of things I want you to notice here. I want you to notice the fact that we are starting with a reactant, and I'm actually going to call it reactant number 2. No, I'm actually going to call it reactant number 1. Left to right, we are starting with a quantity from reactant number 1, and we are going to stoichiometrically convert or stoichiometrically calculate reactant number 2. Now, the reason I'm emphasizing this is for the pure fact that, again, since we are going reactant to reactant, this is also not a limiting excess problem. Okay, so here's our setup. I start with what they give me in the problem, which is 104.7 grams of the nitrogen gas. You will notice that when I do these problems, I have a numerical value, a unit, and an identity. It helps me keep track of my work, and it helps me figure out, it's a roadmap, so it helps me figure out where I'm going. Now, the balanced chemical equation is in the language of the moles. It states that 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas. I cannot use the mole-to-mole ratio here because this is not in the same language as the balanced chemical equation. So my very first step is to use the definition of molar mass to convert this mass of nitrogen gas to moles of. So I'm going to put 1 mole of nitrogen gas is 28.02 grams of nitrogen gas. And again, notice I have number, unit, identity, number, unit, identity. This is just the definition of molar mass. Please remember, this value right here will never be anything but 1. The definition of molar mass is the mass of 1 mole. If you ever make this a 2, a 3, or 4, then you do not have the concept of molar mass mastered. The next step is my stoichiometry part. From my balanced chemical equation, I take the coefficients from the nitrogen, which I am trying to go from, to the hydrogen, which I am trying to go to. And from the balanced chemical equation, my coefficient for the nitrogen is 1. And from the balanced chemical equation, my coefficient for the hydrogen is 3. The question doesn't ask me how many moles of hydrogen gas. If it did, I'd stop right here. It's asking me what mass of hydrogen gas. So again, I have to go to molar mass of the hydrogen gas, which is 2.02 grams. And I multiply the top, divide by the product of the bottom, and I get an answer in, let's see, 1, 2, 3, 4 sig figs here, 4 sig figs here, counted number, counted number, counted number, counted number, 3 sig figs here, so I have to have 3 sig figs in my answer, 22.6 grams of the hydrogen gas will be needed to completely react with 104.7 grams. Now look at this problem. These are two reactants. In order to use up completely 104.7 grams of nitrogen gas, you need 22.6 grams of hydrogen. Not asking you anything about products or anything like that. It's just saying, how much hydrogen would I use to completely use up this guy here? And remember, this part is the stoichiometry. This is the stoich part. This is the only time you use the coefficients from the balanced chemical equation. Yeah, this is a 1, 2, but that's molar mass. This is a 1, but that's coincidental. This is a coefficient. This is a definition. So please keep those straight. It'll make your life so much easier. And also what'll make your life so much easier is if you just remember number, unit, and identity, especially when we're doing stoichiometry. This one is also different. This one says how many ammonia molecules, which is a product, can be made from 1.75 times 10 to the 25 molecules of hydrogen gas, which is a reactant. And then this little line here helps me out tremendously. Assume excess nitrogen gas. Since one of the reactants is in excess, it is not a limiting excess problem. So I like that. There's less work. So it is not a limiting excess problem. All right, so this is going to be a nice snap. Now, again, the actual balanced chemical equation is in the language of moles, but my starting number is not. They start me out with 1.75 times 10 to the 25 molecules of hydrogen gas. Well, I need to convert this to moles. Why? Because the balanced chemical equation is in the language of the moles. I cannot use a mole-to-mole ratio to convert molecules. So my first step is, Avogadro's number states there are 6.022 times 10 to the 23rd molecules, and I'm going to run out of room, but I'll figure it out, molecules of hydrogen in 1 mole of hydrogen gas. This is just a definition. According to the balanced chemical equation, I am going to ammonia, and the coefficient for ammonia in the balanced equation is 2. I am going from hydrogen gas, and the coefficient for the hydrogen gas is 3. Here's my stoichiometry part right here. This is where I used my coefficients from the balanced chemical equation. They're asking about molecules of, and I've got to go from moles of ammonia to molecules of ammonia. And according to the definition, 1 mole of ammonia is going to be 6.022 times 10 to the 23rd molecules of ammonia. Notice again in my work, number, units, and identity. Do the math, and it gives me an answer of 1.175 times 10 to the 25th molecules of ammonia are produced for every 1.75 times 10 to the 25th molecules of hydrogen gas used in excess nitrogen. Now look at the problem. You can see that there's redundancy with this guy and this guy, and you could have just done a 2 to 3 ratio. Next one. This one is an example of mass to ammonia molecules. And what I'm going to do here is I'm just going to give you an answer. So what I want you to do is I want you to set it up appropriately. I want you to determine if it's a limiting excess problem. Tell me yes or no. Set it up appropriately. Okay. To give you the answer for this guy. And what I want you to do is work it out. And I want you to compare, look for proper number of sig figs. Ask yourself, is this a limiting excess problem? Just do the work, see if you come up with this answer, and we will discuss it next day in class. And I'm actually going to cut off here. I'll make this part 1, and then there will be a part 2 to go along with it.